Okay, so now we've looked at electronic structure in the previous video. We're going to now look at ionization energy. Later in this video, we'll see why the electronic structure is relevant to ionization energy. And in fact, actually, ionization energy is one of the pieces of evidence that backs up the ideas of electronic structure that we had in the previous video, this idea of these different sublevels and orbitals. Okay, so what do we mean by first ionization energy? So we're really referring to the energy that's needed to remove the outermost electron from an atom. That's what's sort of shown in the equation that we can see here. So we have gaseous atoms and on the left-hand side, and then we can see that that atom has lost an electron. We've got to keep it in the equation because we're going to make sure that the whole equation is balanced. And when we're balancing equations, we're not just looking at the number of each element, in this case x, that we've got one of x on left and one of x on the right. We've also got to look at the, or consider the overall charge. So if you look at the overall charge on the left, it's 0. And we have to show the electron because otherwise we wouldn't also get 0, because we have a 1 plus charge from the X plus ion and we have a 1 minus charge from the electron. So overall charge. Okay. Now the values to remove one electron from one atom are incredibly small, and what you'll find in chemistry, this is one of the reasons to consider the mole, is that we typically look at any changes in chemistry in terms of moles. So here we're looking at the energy that we're going to be looking at when we talk about first ionization energy is the amount of energy to remove the outermost electron from 1 mole of the atoms, and that measurement is going to be, or the unit of that measurement is going to be in kilojoules per mole. Okay, so just that's what that represents in the green there, kilojoules per mole. So this is a more formal definition. Definition like this would be, in theory, worth 3 marks if a question ever came up. I think in A-levels today, it's less common for an actual definition to be requested for in an exam question. It does occasionally happen, but what I would say is definitions are important because they help you understand what it is you're actually talking about in the context of other questions. So first ionization energy will appear and crop up in much later in the course, and it won't be the only definition that you have to learn or know or understand. And it's really about understanding definitions. That's what's important, and the first part of understanding a definition is to remember it. So the first ionization energy. So what have we got? Anything interesting here? Well, we've got this term enthalpy change. So enthalpy is a word you'll hear a lot more in A-level chemistry, but you can just think of this really as being an energy change. And we'll talk about enthalpy when we do energetics, but you can think of this as the energy changed when 1 mole of gaseous atoms, so we have our gaseous atoms, form 1 mole of gaseous ions with a single positive charge. There's our single positive charge, and of course to keep the equation balanced, we're going to have the electrons there. So there are 3 parts to that then. We've got to make it clear that it's all about 1 mole. We've got to make it clear that we have gaseous atoms and ions, and we have to make it clear that in the case of first ionization energy, we're going from atoms to a single positive charge. The reason they're gaseous is really, if you think about your states of matter and you think about how those particles interact with each other, in gaseous form, those interactions are, well, they're not nothing, but they are much less strong than they would be in a solid or a liquid. So anyway, this like a lot of things in chemistry when we're talking about definitions, they'll quite often be in gaseous form. And we can apply that definition, or the idea of that definition, to successive ionization energies. So we can think about the second ionization energy and the third ionization energy. So just something to be careful or be aware of. In both of these ionization energies, we are again just removing 1 mole of electrons. We are removing the outermost electron. In second ionization energy, we're removing this electron now, not from gaseous atoms, but from the gaseous 1 plus ion to form a 2 plus ion. So these again will be, their values will be per mole, okay, so kilojoules per mole will be the energy values, remember, per mole. And the third ionization, and so on, and we could keep going. We could have fourth, fifth, sixth, seventh ionization energy, but remember, whichever ionization energy it is, we are changing the charge by 1, okay? So in the second ionization, it goes from +1 to +2, and in the third ionization energy, it goes from +2 to +3. So there are 3 factors that affect ionization energy. The first is distance from the nucleus. The second is the nuclear charge, or the number of protons in effect. And then the third is shielding. So this might be ringing some bells, because it was in terms of these 3 things that at GCSE you would have talked about the changing reactivity down group 1 and down group 7. So down group 1, the elements became more reactive, the alkali metals became more reactive, and your explanation of that increase in reactivity was because of distance from the nucleus, the nuclear charge. Well, you might not have spoken so much about how many protons there were, perhaps, and then also shielding would have been something you would have talked about. And equally, when it came to the reactivity of the halogens, you would have been referring to those points also. Now, just before we carry on and look at actual changes in ionization energy, I just want to make it, or highlight at this point, that there is a conflict between some of these factors here, or between these factors. So we will find that sometimes nuclear charge is more important than distance and shielding, and sometimes we will find that distance and shielding are more important than nuclear charge. There's almost a battle between them, sort of nuclear charge versus the other 2. Because nuclear charge is about, a bigger nuclear charge means an increasing attraction. An increased distance and increased shielding means a weaker attraction. So there's a sort of a combat between them. Sometimes in one trend we'll find that the nuclear charge dominates, and in another trend we'll find that the distance from the nucleus and shielding dominate. And hopefully that will become clear shortly. So this is just it's a sort of a pictorial representation of the changes or differences of atomic radii. Let's just make that absolutely clear. So what we're showing here is atomic radii. Okay, so it gives us a sense of the size of the atoms compared to each other. This is groups 1, 2, and then 3, 4, 5, 6, 7, and 0. So it misses out the transition metals. Hydrogen, well, okay, it's debatable whether it's really group 1, but let's not worry about that too much at the set moment. So what we can see is, if we think about trends, and trends are very important for chemistry, as we go down the groups, not terribly straight line, we can see that down all of the groups pretty much. Halogens, I mean, so look at the numbers if it's not so clear from the pictures. So those numbers are radii values. So the radius increases, okay, as we go down. And if we go across, so if we go across a period, the radius decreases. And so these trends are going to be useful and important when we think about ionization energy, because if you remember the 3 factors, one of the factors that affects ionization energy is the distance from the nucleus to the outermost electron, the one that's being removed. So we have to consider things. We have to consider the atomic radii, and the trend is going to be important to explain the trend in ionization energy. So here's here are the ionization values for group 2. So we're going down the group as we go from beryllium to magnesium to calcium to strontium to barium. You can see that the first ionization energy, because that's what these values represent, the first ionization energies for those elements, decreases. So it's much easier to remove an electron from barium, the first electron, sorry, or the outermost electron from a barium, gaseous barium atoms. It would be 500 kilojoules per mole than it is to remove the outermost electron from a mole of beryllium atoms, which is 900 kilojoules per mole. And those two, the sort of blue circle and the purple circle, are there really to represent the change in, or to show that there is an increasing atomic radius when we go from beryllium to barium. So if we now explain why that ionization energy, why the trend is that the ionization energy decreases as you go down group 2, and which will also be the case with other groups, then we can do it in the following way. So it's always important to state the general trend. So the general trend, as we said on the previous slide, is that the first ionization energy decreases down the group. So how can we explain that? Well, we have to focus on the factors that must lead to that consequence. So the atomic radius increases, so the distance from the outermost electron to the nucleus increases. There's greater shielding. You think about your shells. You think about your energy levels. You've got more energy levels as you go down group 2, and so the consequence of that is you get a weaker attraction from the nucleus to the electron in the outer energy level. Now, if we were thinking about nuclear charge, as we go down the group, clearly the nuclear charge must increase because we have an increasing number of protons. But what the experimental evidence is showing us, and the experimental evidence are these values of 900 kilojoules per mole for the first ionization of beryllium and 500 kilojoules per mole for the first ionization of barium, what they are telling us is that the atomic radius, that increase in atomic radius, that increase in shielding is a much bigger factor and trumps, if you like, the increase in nuclear charge. So we then just focus on the factors that lead to this trend that we see here. What about if we go across the period? So what I want to focus on initially is the general trend. So if we were to say what the general trend was across, this is period 3, we would say that it increases. That is the general trend. Okay, the general trend is it increases. Sure, we've got a couple of anomalies. We're going to talk about those. But at the moment, we're just focusing on the general trend, and the general trend is that the ionization energy increases. So how can we explain that? So again, we focus on the factors that would lead to an increase in ionization energy. And clearly, as we go across a period, we have an increasing nuclear charge. So we have an increase in protons. We have the same number of shells, but if you recall the pattern a few slides ago, the atomic radius decreased across the period. So overall, we're getting an increased interaction between the nucleus and the electron in the outermost energy level. Now, I mentioned it very briefly that there were anomalies, and I hope you could see what those anomalies were. So the general trend is an increase across period 3, but we can see that when we go from group 2 to group 3, we have a decrease, and when we go from group 5 to group 6, we have a decrease. So we have to explain that even though the general trend is that it increases across a period, why do we get those two dips? Why do we get those two anomalies? Well, we're going to explain that by thinking about the electronic configuration, something that we looked at in the first lesson. So we're only focusing on the outer energy level, but if you look at aluminium, or if you look at the change from, magnesium to aluminium, we go from 3s2 at the end of the electron configuration to 3s2, 3p1. So that's going to be a factor. And if we look at phosphorus to sulfur, what's going to be important is the change from 3p3 to 3p4. So the reasons or the explanations for each of those changes is actually going to be different, but it is going to relate to the electron configuration that we've considered in our first lesson in the atomic structure topic. Okay, so let's look at the first anomaly. So that's when we go from group 2 to group 3. So on our example here, it's from magnesium to aluminium. But actually, I want to stress this would be true of any group 2 to group 3 element. So we could be looking at calcium to gallium, or strontium to indium, for example, or even beryllium to boron. So just bear that in mind when you're looking at ionization energies, because sometimes in exam questions what they'll do is they'll throw in an element that you're unfamiliar with, but remember, a lot of chemistry is about patterns, so just look at where it is on the periodic table and think about what you know about that period and a change from that period to the next, for example. So when the outermost electron is removed from magnesium, it's removed from the 3s sublevel, and so it's removed from an s orbital. When it's removed from aluminium, it's being removed from a 3p sublevel, or a 3p or a p orbital. And the 3p orbital is at a higher energy level than the 3s, which means it is easier to remove. The electron is found on average further away from the nucleus, and therefore is easier to lose. So that's why we get that dip when we go from group 2 to group 3. The reason for the dip when we go from group 5 to group 6 is a different reason. So in group 6, that's when we've just paired up a p orbital, or electrons in a p orbital, for the first time. Group 5, all of the electrons are in separate p orbitals. So the electron that we're going to remove when we remove the outermost electron from group 6 is going to be one of the paired up electrons, whereas the electron we remove from group 5 is going to be one of the unpaired electrons. And because we're removing a paired up electron, there is a slight repulsion between the two electrons that are paired up, and that makes it just slightly easier to remove an electron from P4 than it does from P3. So if an exam question asked us to explain why the first ionization energy of sulfur was lower than phosphorus, our explanation would be that the electron removed is a paired electron in a p orbital, and paired electrons repel, making it easier to remove one of them. So this just sort of summarizes that. We get the dip from group 2 to group 3 because the electron removed is now from a 3p sublevel, which is further from the nucleus. And we get a dip from group 5 to group 6 because the electron being removed is from a paired p orbital, which is easier to remove due to the repulsion between the electrons. So here are the first ionization energies for the first 56 elements, so it takes us all the way to barium, and we're just going to highlight the trends we've been talking about by looking at these all 56 elements. So if we just say took the elements, or highlighted the elements that are in group 0, so helium, neon, argon, krypton and xenon, we can see that the ionization energy decreases as you go down the group, and we can explain that trend because of the increase in shielding and the increase in the distance from the nucleus to the outermost electron. It's perhaps less clear based on the values here, but it is exactly the same with lithium, sodium, potassium, rubidium and cesium with group 1. We can see that as you go down the group, the first ionization energy decreases, and again because of increased shielding and an increase in the distance from the outermost electron to the nucleus. We can see the general trend regarding going across a period, across the different periods. So there's period 2 from lithium to neon, period 3 from sodium to argon, period 4 from potassium to krypton. We can see that the general trend is that it increases across the period, and we can explain that because of an increasing nuclear charge and because we have a decreasing atomic radius. So this isn't something we've particularly spoken about so far, when you get to the end of a period and you move to the next period, you can see there's a dramatic drop in the ionization energy. So we get to the end of period 1, helium, and we start period 3, and we can see that lithium's first ionization energy is much less than helium's. Again, when we go from period 2 to period 3, we can see that the first ionization energy of neon is much greater than that of sodium. So let's think about our factors. Clearly, if we go from helium to lithium, or neon to sodium, or argon to krypton, we are increasing our nuclear charge because we're adding one more proton in each instance. So that clearly isn't winning the battle, so to speak. What we do have is another energy level or another shell. So we are getting an increase in the distance from our nucleus to the outermost electron, and we are getting increased shielding. And if you remember that image earlier, and you might want to just go back and look at it, of which gave us sort of comparative atomic radii in groups 1, 2, 3, 4, 5, 6, 7, and 0. It was a big difference between the atomic radii of, say, neon and sodium. Sodium was a much bigger atom. So we have increased shielding, and we most certainly have an increase in the distance from the nucleus to the outermost electron when we go from the element at the end of a period to the element at the start of the next period. Okay, so we've looked at the first ionization energies changing from one element to another. So we've looked at it down a group and across a period. But what about if we look at the successive ionization energies of a particular element? So we take the first electron, then the second electron, then the third, and then the fourth, and so on. So again, we're going to talk about general trends first. And if we look at what we've got here, we can see that the general trend is that it increases. Okay, so the general trend is that the successive ionization energies are getting larger. So we've got this word subsequent, so it means after the first ionization energy. So our first ionization energy is here, what I've just highlighted in yellow, and then there's a big jump. So all of the subsequent ionization energies after that first one are being removed from a cation, so that means a positively charged ion. That cation is smaller because it has more protons than electrons now. It is also positively charged, so there is now a greater force of attraction between the electron that's going to be removed next and the nucleus. So we will get that will continue to be the case. That force of attraction will increase as we remove electrons, because the cation will become even more positively charged and it'll become even smaller. And so we have an increasing force of attraction, so our successive ionization energies are greater. So it would help us to look at a concrete element and look at the successive ionization energies of that. So we're going to look at potassium. So we're just reminding ourselves here of the electronic configuration for potassium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If we counted all of those values, 2, 2, 6, 2, 6, 1, we would get 19. That is the atomic number of potassium. So that means it has 19 protons, and if we're starting with a potassium atom, then we must have 19 electrons. So just before we explain this graph of successive ionization energies of potassium, I just want to make a couple of annotations, or make a couple of extra annotations. So the first electron that we remove, at that point we have 4 energy levels. The next 8 electrons after that, we have got 3 levels. And then the following 8, we've got 2 levels. And then finally we have 1 level. Okay. So we can see that there is the general trend is that it increases, but we can see a couple of large jumps. So there is a large jump after the first electron is removed. There's a large jump after the 9th electron is removed. and there is a large jump after the 17th electron is removed. This is providing evidence for the fact that we have these energy levels. So when we go down from 4 levels to 3 levels, we are suddenly now much closer to the nucleus, which is why we get such a dramatic increase in ionization energy, because the distance has dramatically changed. When we go from 3 levels to 2 levels, we also again have a dramatic increase in ionization energy, and that's because again we are now much closer to the nucleus. And then finally, when we go from 2 energy levels to 1 energy level, we have another dramatic increase in ionization energy, and again that's because we have a huge change in the ionic radii. With 1 energy level, it's a much smaller ion, so we have a much shorter distance between the nucleus and the outermost electron, so we have a dramatically increased ionization energy. So it's data like this that has provided evidence for the fact that we have these energy levels. There's one piece of evidence. But it means we can also look at anonymous ionization energy, successive ionization energy graphs, and use our knowledge now to determine what group that element must have been in. So we're going to look at some examples now. Okay, so we could be given a graph like this and be asked which group is this element in. Well, there is a big jump in ionization energy after the 2nd electron has been removed, so when we now remove the 3rd. And then we can see that we then have 8 electrons, and then there's another big jump after the 10th, so when the 11th is removed. So the evidence there points to an element that's in group 2. So we have to remove 2 electrons, and then we get a big jump. So that would be when we were dropping down from 1 energy level to the one below, to the next one. What about the next? Well, why don't you have a think about this? So pause the video, have a think about, well, you've got to do 2 things, okay? So you've got to determine which group you think this element is in, and then you have to justify your answer. Okay, so have a think about that, and then we'll look at the answer. So it's in group 6, and our explanation or justification for that is that there's a large increase after the removal of 6 electrons. So we've had to remove 6 electrons before we've had a large increase. That large increase is when we're dropping down to the next energy level. So we've had to remove 6 electrons before we've dropped down to the next energy level. So the element must have been in group 6. Okay, so those graphs that we've just been looking at that have shown successive ionization energies of different elements, they've all been log graphs. That means that the values, the y-axis has been a log 10 value for the actual ionization energy. If you look at your scientific calculator, you should have a LOG log button probably towards the top right, because we've all got slightly different calculators. If you press that log button, you should be able to, you should get LOG and then a square, a sort of subscript square, which you can put 10 in, because it's going to be log 10. And then whatever your ionization value is, so I'm going to put 496 for the first one. So my calculator now reads log and then subscript 10, and then in brackets it's got 496 because that's what I've put into it. And I've pressed the equals sign. I get a value which is 2.695. So I'm going to round it. So 2.70, okay, to 3 significant figures, because that's what my value was initially given. I'm just going to stick for that for the moment. And if I do the next value, which is an ionization energy of 4563, then I've got now 3.66. And what I'm going to do is, you could just pause the video and do some of the next few values, and then I'll fill in the table. It'll just sort of appear because I'll pause the video and fill it in. But if you want to just do the next few values, and then I'll explain why we bother doing log values for a graph like this. So pause the video, do the next few ionization energies as log 10, and then see if your answers match mine. Okay, so hopefully you got the same values as me. So why would we bother doing this? Well, if you were trying to draw the graph of number of electrons removed on the x-axis and ionization on the y-axis, when you're drawing your axes and determining your scale, you're looking at your minimum and your maximum values. So your minimum value here is 496 and your maximum value is 159079. Now, for you to draw a satisfactory scale that would allow you to plot these points would be horrendous, absolutely horrendous. You'd have all of these values, 1, 2, 3, 4, really bunched together right at the bottom. It would be an awful, awful graph. By doing log 10, we've got something much more manageable. And you will have come across log 10 before. So the pH scale was a log 10 scale. You knew that a difference in pH of, say, 2 to 3 was a difference in the concentration of hydrogen ions, a 10 times difference. It's the same in the Richter scale in geography when you're measuring the size or strength of earthquakes. So when we've got a huge range of numbers and we've got very large numbers involved, it makes life a lot easier to just log those values. So our graph using those figures would look much more like this, which is much more manageable. We can still see the big difference, the big changes between one ionization energy and another. So we can still see there's a big change there and there's a big change there. And this just sort of, this graph just sort of summarizes it. It's another way of representing the one for potassium we saw a little bit earlier. It just sort of repeats a lot of what I said, but it might just give you a different perspective on it. And again, just the same graph, but what we've added to the right-hand side are as a simplification, because we're just focusing on energy levels rather than subshells and orbitals. But it just shows you again, it's looking at those shells, those different energy levels, and we can see how they correlate from doing our arrows to represent the electrons and when we look at the actual pattern of the graph. So that concludes ionization energy. If you have any questions, you know where I am. So please just ask away. Thanks.